4, 3, 2, 1. Main engine ignition and liftoff of the Atlas V rocket with LRO Albatross.
It has been 6 months since NASA launched its Lunar Reconnaissance Orbiter, and the craft has finally entered its long-awaited 50-kilometer orbit. At this altitude, LRO is able to image with a resolution down to half a meter per pixel, as opposed to the 1 meter per pixel resolution of the prior 100-kilometer orbit. This is historically significant because it means that, for the first time since the lunar orbiter missions of 1966 and 1967, we have a craft capable of taking pictures with better than 1 meter resolution. As a lot of you may remember, before the Lunar Reconnaissance Orbiter was launched, propagandists typed about how it would be able to see the lunar module, its legs, the lunar rover, the flag, the ALSAP, etc. But the first photos beamed down instead showed pixelated blobs that are indistinguishable from boulders. Conspiracy theorists complained that these images don't show much of anything and are very poor quality. The propagandists just hyped that LRO had not yet attained its appropriate altitude for mapping, and the resolution would increase once that happens. As one of S-Vector's many sock puppet accounts wrote,
"And when the LRO reaches its final orbit, several miles closer to the surface, the higher detail images it transmits then will still be fake, right? So the whole low-res argument you ASCOTs are fronting now is really just a red herring, isn't it? Isn't it true that you've already made up your minds the images will be discredited by whatever means necessary, just as long as they're discredited?"
There's a laugh. If I was just dismissing photos out of reflex, I wouldn't have even bothered analysing them, would I? It's the propagandists who have already made up their minds to accept unquestioningly whatever brightened craters or pixelated images they can hype over. But I'm not here to finger point. Let's focus on the subject.
Will we in the future get even closer images, better images?
We will get a higher resolution. We're in this commissioning phase orbit right now, which is the elliptical orbit with the closest to the planet, or closest to the moon we get is over the South Pole. That's about 30 kilometers. And at the North Pole, we're about 200 kilometers above the surface. The closest we got to the landing site was Apollo 16, and that was at about 100 kilometers. So at 16, we'll get at least 2 times better resolution, and at 17 and 15, we'll get about 3 times better resolution. And we also, it's very important that we will fly over all these landing sites under different lighting conditions, which allow you to get better views at different types of features. The markings in the regolith, which will show up better when the sun is high in the sky, and then finding hardware on the surface. If we get the sun a little bit higher, right now it's very low, so the signal is low. So it's not only we'll get higher resolution, but we'll get better sun angles as the mission progresses over the next year or couple of years.
What about resolution for Apollo 11 site? You said 16, 15, and 17. What about for 11?
Oh, it'll be slightly better than 2 times better resolution.
Now that LRO has entered its mapping orbit of 50 kilometers, we have the results. Since entering this orbit, the LRO has returned one photo of the Apollo 17 landing site and one of the Apollo 11 site, both with a resolution of 0.53 meters per pixel, and one photo of the Apollo 12 site with 0.49 meter per pixel resolution. I ask anyone to look at these images and tell me just how the hell are these any better to the ones we had before? At least in the case of Apollos 11 and 12, we see something that even remotely resembles footpads, but at the end of the day, they still just appear as white blurred pixelated blobs. And as for the surrounding landscape, there's even less to be impressed about. For example, here's an earlier Apollo 11 scene taken at 100 kilometers. Now here's the latest one taken at 50 kilometers. The new image is double the size because it's half a meter per pixel. Now granted, more Apollo relics come into view, and the LEM now has legs. But the landscape doesn't show better resolution. Actually, it looks worse. Are these really the oh-so-high-resolution proof-positive images we waited for? Pardon me for sounding ungrateful, but that's ridiculous. Images taken from only 50 kilometers up, and with a resolution of 0.5 meters per pixel, should definitely come out clearer than this, as you are about to see. No doubt, unbeknownst to many who are now hot and wet over these poor-quality LRO images, is the fact that orbiting Earth right now is a reconnaissance satellite called GeoEye-1, owned and operated by a private company, GeoEye Incorporated. It resides at an altitude of 681 kilometers, and its camera has a resolution of 0.41 meters per pixel. This is virtually the same resolution as LRO's camera. Let's have a look at some photos from it. Here's a photo of Rome, taken by GeoEye-1. If we zoom in, it becomes immediately obvious that GeoEye has perfectly resolved cars, buses, even individual people walking the streets. Here's another example, this time showing Quelimine Seaport. Again, we can resolve cars, and even shipping containers and tiny boats. I didn't look at all the images, but there are many of them that perfectly resolve puny objects like cars and trucks and buses. The LRO pictures look even more pixelated than before compared to these. I like this photo in particular because it really pones NASA's arse. Here, we see a GeoEye image of Cape Canaveral, showing one of NASA's shuttles on the pad. The image not only resolves the tiny cars, but also the shuttle stack. Oh sure, a space shuttle is much larger than a car, but we can clearly resolve the nose cone of the solid rocket booster. Each solid rocket booster has a diameter of 3.71 meters, and there is not a single doubt that that's a solid rocket booster. And how about the cars? Cars on average are about 4.6 meters long, and we can clearly make out the windscreens, windows, hoods, trunks, etc. The descent stage of the LEM is 4.27 meters wide, 9 meters wide if you count the landing gear span. But all we can see in these photos is white pixelated junk. By any definition, the lunar modules should be immensely clearer in these LRO images. LRO was 50 kilometers above the lunar surface when taking these pictures, and GeoEye-1 was over 600 kilometers above the Earth when it took its pictures, and yet its pictures are clearer than LRO's. If GeoEye-1 was even closer to the Earth, the detail of the cars would be even more distinctly resolved. And you don't have to take my word for it. I emailed Lisa Dykes, the satellite imagery manager on GeoEye-1, who had this to say.
To answer your query, yes, if the satellite was orbiting the Earth at a lower height, then the pixel resolution would be better, and you would be able to distinguish more detail. However, the lower the satellite is to the Earth, the longer it would take to image the same site, and at this height it revisits once every 4 days on average, as it would have a bigger path to orbit. There would also be more friction on the satellite as gravity forces are in play, thus it would take more fuel to keep the satellite in the same orbit. Atmospheric conditions would also interfere with the clarity of the imagery captured. Most optical satellites orbit in the 500 to 700 kilometers above Earth range.
Okay, sure. You'd get those atmospheric problems in Earth orbit, but the Moon is different. Its lower gravity means the orbit is slower, which allows for better focus without motion blur, and no atmosphere to mess up the imagery either. The fact remains, the closer you are, the better the imagery is. To be more specific, the resolution of such a camera at 50 kilometers would go down to 3 centimeters. So alarm bells should definitely go off in one's head when a camera aboard a reconnaissance satellite orbiting nearly 700 kilometers above the Earth returns better pictures than a spacecraft orbiting only 50 kilometers above the Moon. If a private company can afford a camera like that, then Deep Pockets NASA can do likewise. Had they installed one, it would be sending us pictures of stones 1 inch wide. Not only could we better see the artifacts, we'd also see newly discovered landscape that would have been unknown and hence impossible to replicate on Earth during the Apollo era.